Thank you. So first of all, thank you to the organizers for organizing this wonderful conference and for giving me the opportunity to give this little talk on binomial complete intersections. So this is joint work with my supervisor Samuel Lundqvist and with Lisa Niklasson as well. So let's get going. So let's begin with some motivation. So throughout this talk, I'm going to be working over a ring over the complex numbers, and we will be interested in complete intersections. So when I say a complete intersection, I mean Artinian complete intersections as, for example, defined like that. And I want to know more about these complete intersections. So study them in general might be a little bit hard, but in some more easy examples, we do know stuff. For example, in the monomial case, we know a lot of nice properties about these monomial complete intersections. I mean, we have a vector space basis for these algebras given by all of the monomials not divisible by the xi to the di that appear in the monomial complete intersections. This vector space basis will be denoted like this m v1 to dm. We will see more of that guy later. Other nice properties that we know from monomial complete intersections is we know that they have the strong Lefschetz property. Yeah, that is nice. And we can also describe their Macaulay dualiator very explicitly by just this one single monomial. Okay, so we know all of this nice stuff for monomial complete intersections. So what if we try to go a little bit further and including, say, one more term in each of our polynomials? That might seem like a logical next step to try and understand. So that is, we want to see what happens for binomial complete intersections. So what is known in that case, one may ask them. So we want to study a specific class of these binomial complete intersections. So those of the form where the ith polynomial in this complete intersection has a non-zero coefficient in front of xi to some power. So in the ith binomial, we want to have the pure power of xi to appear. Okay, why would this be interesting to study? Well, it's because there are already some known stuff about these classes of binomial complete intersections, at least in the quadratic case. So we have the following theorem from Harima, Washi, and Watanabe from 2020 that says if we are in the quadratic case and this I here is a complete intersection, and moreover all of these second terms in the binomials are square-free, then the square-free monomials, this that we denoted M222 from the notation from before, this is a vector space basis for the quotient. So we have the same vector space basis as for the corresponding monomial complete intersection in this case. And moreover, they, in the same article, they give a specified determinant in these variables ai and bi that gives criteria for exactly when this ideal I determines a complete intersection or not. That is, they give the irreducible factors of the resultants of this ideal. So we want to try now and see if we can generalize some of these facts to binomials of normal form of higher degree, say. So that is what I'm going to talk about now. So we have three main results that I want to mention related to a monomial basis, their Macaulay dual generator, and the resultant of such ideals. But first, let's really make sure that we understand what this class of binomials include. So we say that a set of homogeneous polynomials f1 to fn of some degrees d1 to dn. They are on normal form if the coefficient of xi to the di in the ith polynomial, this is non-zero. So in the class of binomials, this would give us families looking like this, where now these are homogeneous binomials of normal form, and we assume that all of these AIs should be non-zero. And then we are interested in, okay, how does these families behave like in terms of these A's and B's? Can we say something like when or do they determine complete intersections in terms of the A's and B's, for example? So to be even more specific about what kind of polynomials appear in these families, we can have that this is an example of such a family. We can have mixed degrees, and we can have, for example, two pure powers appearing in one of them. All of that is okay. And being even more explicit, we are allowing stuff like with coefficient, and we are allowing the B's coefficients here to be zero. So in particular, monomial complete intersections are part of this family. But we do need some pure powers to appear in the binomial, so this last guy is not allowed. Okay, but now the question is, how are we going to study these families of binomial complete intersections? Well, the following will be our main tool for trying and understand them. Something that we like to call the reduction graph. So what is that? Say that we have a family B here of binomials of normal form and fix some integer d. Then we want to construct a directed labeled graph, GBD, that we call the reduction graph. And this reduction graph should have a vertex for each monomial in this degree d. And then we let the edge set be given as follows. So we take some vertex corresponding to a monomial. If that monomial, rather I should say, look at the smallest I for which xi to the di divides that monomial. If such an I exists, divide it by that guy multiplied by the mi. And this xi to the di and mi are those determined by our binomials. And if no such I exists, then there is just no edge going out from that one vertex. So what are some properties of these reduction graphs then? Well, we have the edges here, and then one can see that if we have an I-labeled edge going from one monomial to another in this graph, then these two monomials will be related by the following equality. That is, modulo all of the fi's, they will be multiples of each other. Okay, that's good to know. What more can we say about the structures of these graphs? Well, recall that a sink in a directed graph is a vertex with no outgoing edges. And we see that from the definition of these reduction graphs, a monomial here corresponds to a sink if and only if it lies in this set m d1 to dn. The monomial is not divisible by any xi to the di. And otherwise, it has exactly one unique outgoing edge. So if we start at any monomial in this graph and try to follow the unique outgoing edges as long as we can, we will either end up at a monomial in this monomial basis m d1 to dn, or we will find a directed cycle. And these two different possibilities will determine, it turns out, a lot about what happens with the monomials in the quotient by these guys if they determine a complete intersection. But let's take an example just so we understand how this may look like. So say we have the following guy B here, determined by 3 binomials on normal form. Then the reduction graph in degree 3 looks as follows. So here in degree 3, there is only one monomial in this set M222, being this x1, x2, x3 guy down there. So from what we said before, we know that any monomial here will either have a directed path going down to that guy, or they will have a directed path going to a directed cycle, as in the other component. Okay, so what can we now say about these guys? Well, we have the following theorem. Say we have B a complete intersections of binomials on normal form of some degrees d1 up to dn. Then the corresponding monomial complete intersection basis, m d1 to dn, this will also be a vector space basis for a quotient here in the binomial case. So how could one prove something like this? Well, the main lemma that we needed is the following. So say we have B as above and look at some monomial m of degree d. If the directed path in the reduction graph starting at m leads to a cycle, then we can show that this monomial that we started with is in fact in the ideal. That is, in the quotient, this guy is just 0. So we know that if we look at any monomial, then either it goes to a directed cycle and it reduces to 0, or it has a directed path going to some guy here in the basis, and then we can even describe explicitly what multiple of that basis element it will be by just seeing what labeled edges to use in this graph to get to it. So this shows that this guy md1 to dn spans, and we know it has the right size, so it's a basis. Okay, so that was this on the monomial basis part. Let's go on and say some things about their Macaulay dual generator. See if we can describe what the Macaulay dual generator can be. So first, we have seen Macaulay dual generators a couple of times this workshop, so maybe I don't need to say so much about this. We have the annihilator. We let R in the small variables act on the big variables this time. And we know complete intersections are Gorenstein, so we know that there are some Macaulay dual generators for us to find. And moreover, in the monomial complete intersection case, we can determine this guy very explicitly. I am not really aware of any other kind of families of polynomials where I can actually get this Macaulay dual generator that explicitly. But we give a sort of explicit version of it for all class of binomials on normal form. But we'll see if you agree that this being called explicit is enough for when you see it. So how do we find this guy? So we know that we have some f that we want to find, and this f has some coefficients that we need to determine. So what we need to do, well, we'll let our little binomials act on it, and we want this guy to be 0. So that is, we want these coefficients here to be 0. But now we need to see what is the relation between these C alphas and C betas that appear here. Well, what is actually happening? We start at some monomial big X alpha. we differentiate with respect to xi to the di, and then these other guys say that whatever we then end up with, if we multiply by mi, we should get back to the beta. So what I'm saying is that we start with something. If we can divide it by xi to the di, then we do that, and then multiply again by mi, then we get the beta. But this was exactly the procedure that determined edges in the reduction graph. So we see that we need at least this equality for every I-labeled edge in the reduction graph. In general, there are more criteria that appear here than those appearing in the reduction graph, because in the reduction graph, we needed that this I was corresponding to the smallest xi to the di, which divided it. Here we can have more than that corresponding to relations like this. However, in the complete intersection case, it turns out that just looking at edges coming from the reduction graph and their corresponding relations here, that will suffice. So we get the following, at least algorithmic way to determine the Macaulay dual generator. So say we want to determine the coefficients of f here, and b is our binomials of normal form as usual. Then the coefficients can be determined from the reduction graph GBD as follows. So d here being the Sockle degree, we have only one special guy, this x1 to the d1 minus 1, xn to the dn minus 1, that corresponds to a basis element from our monomial basis that we had. So this guy will be special. To determine the coefficient of this guy will always be non-zero. And to determine exactly what coefficient it is, we know that, okay, a lot of paths will go down to exactly this guy in the reduction graph, because we know either we have paths going to this guy or we have paths going to circuits. So we just say, okay, how in all of these directed paths leading down to this guy, how many I-labeled edges do we at most go through in one unique directed paths leading to it? And then we let this number be the coefficient of all the a's here. And then we need some multinomial coefficients to normalize it. Okay, so then that is the coefficient of this guy. And then what other kinds of monomials do we have? Well, we have those who has a directed path leading to this special vertex. And to determine what coefficient this guy has, we'll say that if the path going from this one monomial to our special vertex uses some number ri of I-labeled edges, then we need to change ri over a's for some b's. And that's it. And what should we do with those going to a cycle? Well, as more or less suggested by the monomial basis case, we can take all of those to be zero. And that's it. That's an algorithm for if you see can write down this reduction graph, then you can determine the Macaulay dual generator fairly easily. Let's take an example. So take our same guys from before and the same graphs here in degree 3. So now we have our special vertex here, x1, x2, x3. And we want to first say what is the coefficient of that guy in the Macaulay dual generator. So then we look at all the paths leading down to that guy. Well, we have 2 one-labeled edges at most, 1 3-labeled edge, and 1 2-labeled edge. So the coefficient of that guy will have a1 squared, and then 1 a2 and 1 a3. And if one, for example, want to try and determine some other coefficient, say of x1 squared x3, then we see that in the path from this guy down here, we use one label edge, one free label edge. So we need to change one of the A1s to a B1, and the A3 to a B3, like this. And now one can continue like this for all of the other monomials in this component leading down to the special vertex, and the rest of the guys had 0 coefficient. And here we have the Macaulay dual generator for this guy, in the case when it is a complete intersection. Okay, so that was the Macaulay dual generator part. But now I want to go into the resultant, because now, so far, I've mentioned 2 results relating to when binomial ideals in normal form like this are complete intersections. But it would be nice to know some easy criterion for when they actually do determine complete intersections. So let's try and see if we can do that. So take our standard example, we want to know when do they determine a complete intersection. Well, one small thing we can note quickly in this case is, okay, all of the second terms in all of binomials are square free, so we need at least all ai's here to be 0, as otherwise the point with 1 at the ith component and 0 everywhere else will be a common non-trivial 0 of them. Okay, but I mean, for general choices of A's and B's, they will determine a complete intersection. So we just need to find what are the equations that say, in this case, you are not. And that is when the resultant shows up. So the resultant that we will denote res of f1 to fn in the coefficient, this is a polynomial in the coefficient of our f's, that is in the A's and B's, with the property that this guy is non-zero if and only if they determine a complete intersection. I mean, there are algorithms for computing these resultants, but doing it by hand is not so easy. So we want to see if we could find some easier way to calculate these resultants, at least in our case. So we made use of one standard way to try and calculate resultants, where one do as follows. So let in this case, be the so-called degree plus 1, in the case of this being a complete intersection, say. And then one can partition all the monomials in this degree by saying, what is the smallest xi to the di which divides a monomial here? By the choice of the degree, such an I will always exist. Okay? And from this, one can construct some big system of equations, and this guy will correspond to a square matrix, who we know that by general theory of resultants, the resultant will always divide the determinant of the big matrix that comes from this system. However, in general, this determinant might be a lot larger than the resultant, and if one wanted to try and actually determine exactly what the resultant is, one would in general do this for several matrices of the same type. But in our case, it will turn out that one single guy will suffice. So let's take a look at how this Cn might look like in our case. So for our standard example, we are looking at this guy lying in degree 4, so we will have a 15 by 15 matrix, looking something like this. So okay, one can write out this big matrix, see that the determinant given here, and the resultant one can calculate, for example, using Macaulay to be the following polynomial. And yes, the resultant does divide this determinant, but the determinant is slightly bigger. However, they do contain exactly the same irreducible factors. And that's the only thing that is interesting to us. I mean, we only want to know when this resultant is 0 or not. We don't care if there are squares appearing or not. So Okay, that all of these a's appear, that was what we said from before. We know that. The interesting part is this binomial factor that appears. So we wonder, where do they come from? How can we try and determine exactly which binomial factors we have? So one thing one can do is that these matrices are kind of special. They are, these binomial factors can appear if one does as follows. So take some element here in the matrix, say this A1 over here. Then in this row that we have A1 in, there will be a unique B1. Okay? But now in the column where B lies, there will be a unique A. And then continuing like this, in this row there will be a unique B, in this column there will be a unique A, and continue like this, we see that we found ourselves a cycle or circuit or whatever you want to call it. And this little circuit that appears here, one can show that this guy is exactly giving us the binomial factor that we had. So we had 1A2, 1A3, 1B2, 1B3, same guy as we had here. So that's all good and nice. But haven't we seen cycles like this before? I mean, we saw cycles in the reduction graphs. Maybe they have something to do with this business in the matrices as well. Maybe they do. So say the following. In our reduction graph, and we see a cycle, then we can to that cycle associate what we call a cycle polynomial. So we say from a cycle, we define a polynomial like this, where Ri is number of I labeled edges in the cycle. And then from this, we can define a cycle polynomial of the whole reduction graph by just taking the product of all of the cycles that appear in the graph of these cycle polynomials. So how does this look like in our standard example? So now we need to look at it in 1 degree higher than we did before. So in the reduction graph for these guys in degree 4. Then we have the following graph. Of course, we are in 1 degree over the Stockholm degree, so we know that all of the paths need to lead to directed cycles, as everything must reduce to 0 here. So we see 2 directed cycles appearing here in this case. One guy here with a 2 labeled and a 3 labeled edge, and one guy over here with a 3 labeled and a 2 labeled edge, giving the following cycle polynomial for the graph. And this guy is the same binomial factor as we saw from before. And that is no coincidence. We were able to prove the following. So say we have our standard family of binomials on normal form, and assume for now that all of these mi are not a pure power of a variable. Then and d being the so-called degree plus 1. Then the irreducible factors of the resultant is exactly the same as the irreducible factors coming from this determinant, and that one can also calculate as the product of all the a's and the irreducible factors from this cycle polynomials of the graph. That is all the unique cycles polynomials that come from the graph. So, for example, in our case with the f1s, f2, f3s here, all of these give us a1, a2, a3, and this one binomial factor. I should say that in the case where we do not necessarily assume that all the mi's are not pure powers of a variable, we can still prove that the irreducible factors of the resultant and the irreducible, and this term here, the a1s to an's and the irreducible factors of the cycle polynomial, that they too coincide, with the small little caveat that some of the ai's may no longer appear. So we had that in that case the irreducible factors of the resultant are some product of A1 to AN, and then these binomial factors. Okay, but with that said, let's make some small questions we have related to all of these constructions to end with. So first of all, we have looked at binomial complete intersections now on normal form. So the question is, can any binomial complete intersection be presented as a binomial complete intersection on normal form? That would be nice to know. However, this is not true in general. For mixed degrees, we have an example showing that this cannot be done. However, in the equigenerated case, we do not know. We have an example where we haven't been able to do it, but we at the same time don't have a proof that it can't be done. So that would be interesting to know. Another thing that one might say that, okay, now we have done a lot of nice stuff for binomials. So we were able to go from monomials to binomials and prove a lot of nice stuff. Can one go further? Can we include one third term in our polynomials? In general, no. So the following three guys do find a complete intersection. They are on normal form as we had defined it, but we do not have our nice monomial basis anymore, as, for example, we have this relation. Okay, but doing a generic change of variables to these guys, this guy of these square-free monomials will be a basis. So this leads us to a question as follows. Do every complete intersection have this m d1 to dn as a basis after some change of variables? I mean, this was first asked in the square-free case in the same paper that Jonsson and others did. But looking at our results, we find it general to ask, in general, if this guy can always be shown to be a basis after some change of variables. We don't know. Okay. And finally, this is our conference on Lefschetz properties. And I mentioned in the very first slide that yes, monomial complete intersection do have the SLP. Can we do anything for our families about that? Sadly not. So we know what SLP is, and we know that, okay, we have found a nice monomial basis. We have determined more or less how the Macaulay dual unitary look like. So maybe we could analyze the Hessians to determine SLP. But we haven't been able to show that these matrices are necessarily non-zero. So, but that would be nice to see if someone could use this and go further in that direction and see how do these matrices actually look like and such. But that said, all of the examples we have tried have had the SLP. Even when we specify our coefficients A's and B's to no longer give complete intersections. So we take our forms like determined by these reduction graphs, and then yeah, in general they will determine complete intersections, but for some A's and B's we have criteria where they don't. But even in those cases, this, at least for the few examples we have tried, have had SLP. So that is one question. Do all algebras determined by such form have SLP? Then finally, of course, just having a square-free monomial basis is not enough for having SLP. There are examples in the negative for that. So one needs more than just the square-free basis that we have proved that our algebra has. And that should be it. Thank you.